welcome to this our ultra scalable wireless access USWA webinar. We have the second results webinar now starting. My name is Mika Lasanen. I work at VTT as a project manager and I'm leading dissemination work in this project. So in this slide we have a project consortium and also project duration. So we started in late 2022 and we have still one year to go. So we will end about November 2025. And we have project partners from many countries, Finland, Germany, Spain, Austria and Turkey. And we have companies from wireless communications technology and DECT-2020 development, and also many industry and companies to apply this technology. So we have both technology and application side there. And then our activities are summarized with this slide. So we are focusing to this new standard called DECT-2020, new radio, standardized by ETSI. And we started the project by system architectures, application requirements, and use case definitions. This work has been done already, and you can see some results from our previous webinar. Then we are making research and development for IoT mesh network solutions, and also for ultra reliable and low latency mesh networks. Today we will have presentations related to these activities. Then we are also developing proof of concepts. There are different types of proof of concepts listed there. For instance, we consider energy networks, industrial conditioning monitoring, and industrial IoT, and then this kind of ultra reliable low latency mesh networks also as an example. And as parallel activities, we work for standardization and market analysis and exploitation. Then we go to program. So we are now in welcome and introduction. Then we will have a presentation on standardization landscape. Your Pirskanen project coordinator will give that. And then we will have 4 other presentations that we will introduce. Then when they come. Okay, we will be starting. So please, Juho.
So this is the DECT-2020 new radio standardization landscape. So the original plan was that Jussi Numminen, ETSI DECT vice chair, would have given this, but unfortunately he was called to some very urgent standardization activities regarding DECT-2020. So he traveled there and he's somewhere in Europe now, if I recall correctly, in Amsterdam. But so I promised to give the presentation instead of him. Basically, trying to go through DECT-2020 new radio standards introduction, set of standards what we have, and then a little bit about the key features, mainly on the release 2. And basically, the DECT-2020 new standards has grown quite significantly since last presentations in last webinar and so forth. So, but let's say there is a quite nice structure of different things. So the first part, of course, is the core standards. So the TS103, 636, and from parts 1 to 5. So the first part is the part 1, which is this kind of overview, nice reading for everybody. Shouldn't be that technical. You get the overall understanding of the whole technology. And then we go to the deep dive in the actual specification and technology definitions in part 2, which is containing the radio reception and transmission, emission masks, transmission power requirements, receiver sensitivity requirements, and so forth, and how different operating bands and channels are arranged. The part 3 contains then the physical layer definition, how the OFDM modulation is used for transmitting packets, transmitting data over the media, and how the receiver works, how the turbo coding, channel coding, and so forth works. In part 4, then we cover the medium access, so how the actual transmissions are controlled, what are the procedures, how to set spectrum, and how the connections are established, and how the control signaling is done. And then in the part 5, we cover the data link control layer and convergence layer, so basically protocol layers above the MAC, what services are provided to the application layer. So, for example, application can be IPv6 data or directly application data from the sensors or other devices. What are the steps and how the protocol provides support for different services. So, for example, in the MAC layer we have a link-specific security, but in the convergence layer we have an end-to-end security between multiple, even in mesh network with the multiple hops and different functions so that the different data types and data services, data amounts can be converted to the suitable suitable data PDUs for transporting through the wireless links. So the release 1 has been published. The latest version of the release 1 is 1.5.1, which is published in March 24 by ETSI. So that's a bit more than half a year old publication. So there has been previous publications, of course, for release 1. And then the new set of course specification is the release 2, which was published in October this year. So a bit more than or roughly a month ago, which contains now a set of new features to the core standards. And the main features that we then discuss more on release 2 are the support of very low power devices, configuration data distribution, access without security credentials to enable radio device authentication and key distribution, downlink routing improvements, and automatic IPv6 address configuration. And then on the release independent side, we have a radio and protocol conformance testing specification work ongoing. So those are not yet published, but they are at the moment development under development. The target timeline for the first publication of those is in second half or first half of next year. So in summer time frame. A bit more than 6 months needed for the completing of those. For the first publication, of course, the work will continue on those. Then we have a regulation of compliance set of documents, which I will talk a little bit later more. So the first one is this harmonized standard. So this 301.4.6 part 2, which is the harmonized standard for DECT new radio equipment compliance, and that has been published in August 2023. So that provides means for making the minimum tests for all the devices and then placing devices in the market inside EU and then also in some other regions which are referring to in their regulation to this standard, for example, Australia. And then we have published also, ETSI has published TR 103 943, which is the system reference document, which is like providing information to the regulation bodies in Europe of this technology and how new spectrum can be allocated for this technology, and that's we cover a bit later. And then we have a application-related material already now published. So the part one is the overview. So there's a similar kind of structure of specifications as in the core standards. So this TS103874 series covers different application-related definitions. So the part one is the overview, similarly overview as part one in this core standard. And then we have a part two, which is covering configuration and parameters to be used for applications covering smart metering, city and building applications in mesh operation. Or the mesh operation is basically assumed to be used there. And then we have a IPv6 profile in part 3, which is basically presenting how to utilize the release 2 features of the core specifications for IPv6 and how to do the automatic IPv6 address configuration so that you don't have to request the IPv6 addresses to the from any like any servers. Rather, device obtains the correct IPv6 address automatically when being part of the mesh network or DECT-2020 network in general. And those were published also in actually the smart meter was published in June, and then the rest of were published in October 24. So this is basically the set of specifications. The new part of new release, significant new part is the release 2, and also the application-related standards. And there is an intention that the release 1 specifications might receive some updates based on the corrections around still, but the new features are then done in release 2 or even further in release 3. So then what is active work items ongoing at the moment? So there is, as mentioned, this conformance testing, part 1 and part 2 for the radio transmission and reception testing and the radio protocol testing. And then we have a new part 4 application specific profile, which is describing how to utilize over the air, how to utilize core specifications for over the air software update operations, and defines the minimum requirements for the devices so that in systems, large mesh networks, for example, the over the air software update goes smoothly through. So that work is ongoing. Additionally, we are maintaining this kind of work internal ETSI internal work item for technology roadmap, which is updated and potentially published later. And then, of course, the release 2 has the maintenance work. So, of course, there might be some places where we need improvements to the standard and clarifications. So we maintain the both core specification release 2 standard, but also the access profile standard. And then we have a few study items ongoing. So the study of radio spectrum and related technical requirements, basically for DECT-2020, basically considering different spectrum areas, new potential new spectrum bands where the technology can be used, what would be the requirements on those bands. Then we have a study on information elements for network cooperation, so how we can utilize same spectrum but share it more wisely manner between different applications. And then how to study on optimizing scheduled access. So basically when you have this kind of very frequent transmissions which are occurring long time, for example, in 10 millisecond or 5 millisecond or shorter periods, and they are happening very frequently, can we optimize the physical and protocol layer for that kind of services. And then study of additional functionalities is ongoing, so for the release 3 and so forth. So those are the activities. So if we look from the time schedule point of view, or this kind of how the years and how we see the future coming, so basically we can see that in the previously we had the release 1. It was covered in the ITUR recommendations from parts 1 to 4, and then in the part updated recommendation, all the parts 1 to 5 were covered. And then we see in the future that when ITUR is making a new revision of the recommendation, this M2150-3 version is coming out. Also the release 2 is covered in that recommendation. The release 2 study and the specification now is basically done. There is still, of course, the correction round and this kind of improvement round ongoing, but the main work has been completed. The release 2, the release 3 study of new functionality, what new features would be good to see in release 3 is ongoing or started, and the specification starts later. And then if we think about the harmonized standard, and so that was already published in late last year. Now we are going for the first publication for the conformance testing during mid next year, roughly. And then application profiles, first sets are published now. Second round of publications and second set of application profiles are to be foreseen. Then if you go to the release 2 features, basically, as mentioned, the first feature is to support very low power devices. So there's actually two functionalities introduced to support those. So basically in the release 1, we assume that the device or the design is that the devices are mainly having enough energy in the battery or are mains powered, so that this keeping the receiver open, let's say basically constantly is okay for the devices. But now we introduce this kind of very low power devices. So the first one is that the uplink data transfer without association. So basically now we can have in mesh network or in the independent of the network architecture, devices that are not in the mesh network, not routing data, other devices data, but they are silently being part of the network. They don't receive anything, they don't be active, but when they have some data to transmit, they basically can send the data without even doing the association. So they just send the application data to the next hop, which they have detected in the network. And then routing device receives the transmission and without association and sends the acknowledgement and starts the normal data routing process to the backend, and the device who was sending the data can go to the sleep. So this can enable like applications like water meters, which are, let's say, from the regulation point of view, not allowing to have a lot of energy and mains connectivity. So and also other type of devices, like even going to the asset tracking nodes that they are regularly sending like health information only to the backend service. Then the second part of the feature is this paging support option and association lifetime. So So as mentioned in the release 1, we assume that the devices are monitoring the cluster beacon for paging and indicates the RATS resources for downlink transmissions. So now we basically in the release 2, the device may make the association on for long periods, not following anymore the beacon, but they are basically polling the downlink data with certain periodicity, and the periodicity can be adjusted based on the application needs. So the device is connected basically to its next hop. Downlink data can be routed to the next hop, but then the device is not constantly receiving, or it's only receiving when after the sending the polling request and then obtaining the data. So by this and the previous feature, we can also provide like a low power device, but also the downlink connectivity for those devices. And of course, you can mix and match the previous functionality and this functionality. So you might have a device that is long time without not having even association, is sending only periodically data, but is, for example, once a day or what given periodicity establishing the association and then requesting by polling the potential downlink data and, for example, downlink configurations. And then, of course, if there's a really need for significant downlink capacity, it can change the activity to the normal release 1 activity, so that the high amount of downlink data can be pushed to the device. So this is the first part of the release 2. The second part of the release 2 then goes to the higher layers. It's not anymore MAC functionality. It's a configuration data distribution. So basically, it is optimized to configuration data information delivery in large-scale mesh networks to minimize identical information delivered from backend to individual devices. And this is, for example, now used heavy, and this is the functionality how we can optimize the IPv6 address configuration in the devices. So the configuration data distribution is used there to distribute the prefixes and IPv6 prefixes and the information how to device can obtain its own IPv6 address in this part of the network. But also this can be used for other functionalities like this over-the-air updates. So managing that information, that what software is to be downloaded and other application data configurations. So you might have for example, you can easily manage the data. For example, if you have thousands of devices in your system that are reporting some values periodically, you can configure that what are the periodicities of these data applications, and you don't have to configure each node individually. You can make, for example, group of devices to use, or say same devices with same application to use same periodicities if you like. So basically, this application in the route info is used there, which is already in the release 1, to identify that, okay, now the configuration data is changed, and then the device is sending request to obtain that data, and then receives the money, the actual data in multiple downlink, one or multiple downlink transmissions, and this functionality is covered in the part 5 core specification. And then when the device obtains, for example, from the sink or the gateway the information, it starts to broadcast the new data availability into the next hops in the system. So it distributes the information inside the mesh network. Then the second release 2 or the third release 2 feature, which is important for the devices, how to configure devices, how to get the devices in part of the networks is of course the access without security credentials for the so basically there we introduce let's say again on the top of the basic MAC and the DLC and the convergence layer functionality, which is introducing a client, proxy, and a server functionality. So basically, the provision client is the device who wants to authenticate to the system. It doesn't have the security credentials of the MAC protocol or the CVG layer protocol, so it doesn't know. It just sees that there's a network where it can join. The proxy device in the middle part is basically controls this process by transmitting joining beacon or joining information in the beaconing messages. So basically, it enables that indicates by itself first that devices who are not having security credentials can try to can join to me or associate to me for the security procedures, and then basically it forwards only this security messages coming to the certain endpoint to the rest of the network. So if something other data is transmitted to the device by the device who is joining, it will filter that data away, but those messages coming to the endpoint, it will forward to the backend server, and the backend server will then do the authentication of that device, which is having that client functionality and is joining. And this is like enabling the different data forward method, the actual what is the authentication protocol then, and what is this like a preset key, or is it public private key based method is left open for this. It can be different for different applications. We foresee in the ETSI DECT that there will be a new functionalities defined for different authentications on top of this. But currently it has left to open for so that different industry players can select different methods. It just enables this and forwards data. And in the star network topology, of course, the only difference is that basically the provisioning server and provisioning proxy are in the same part in the device, or you don't really have the provisioning proxy which is forwarding the data, because the data directly from the device goes to the provisioning server. But works so it works in all architectures, and it works for any authentication protocol then to be used. Then we have a separate presentation actually for downlink routing and downlink improvements. But basically we have for downlink we have two features. We have a cached downlink routing, which is basically opportunistic method for improving the downlink routing decisions. On currently, this is the selective flooding functionality. So basically the radio device in FT mode learns from the uplink data that I'm receiving this device, the original source of the data is this device. I'm receiving it from this member. So if I have data to this device, I send it only to this member, and it's a completely backward compatible. Only set of devices can use that one. And other devices don't really understand that is being used, because it just restricts the transmissions. Of course, there's a time and mobility sensitivity. So if the devices underneath are selecting new routes, the decision may go wrong, or you need to be careful that you don't use the old information too long. And then we have a selective source routing, where the devices are registering basically to the root or the sink, And the main functionality here is that then the sync can decide where to send the data, and it can tell in the routing PDU how to forward data in the next hops also. The good part here is that we have made it so that we don't have to do it in complete network, so the depth, how far you need to do it is also can be controlled by the beaconing, so you don't have to do it like endlessly in the all the depth of the network. You can do it only on the limited set of hops from the sync onwards, which then limits the number of registration signaling, and that can be optimized. The number, the depth of the selective source routing can be optimized depending on the environment, depending on the how devices are expected to move and change the next hops, and how let's say many hops you want to use this. Do you use it only in the sync and then the second hop level of the hops, or do you use it further? And then of course design has been such that of course they can be both used simultaneously, so you can use the selective source routing and cached routing in the same time in the system. Then going to the optimized IPv support, basically currently already in the release 1, the IPv6 was more or less supported from the how you get the PDUs going through to the protocol, but now we optimize it for the IPv address configuration. So basically now in the network, the IPv6 address configuration provides autonomous IPv6 address generation by the nodes in the mesh network. Basically, as said, it's done so that this configuration distribution is disseminating the prefix information from the sync to the every node to the network. So you know the first part of the device obtains from there the first part of the IPv6 address, and the last 64 bits are always generated so that you have the sync address, which the device also obtains when it's associated with next hop, and then the 32 bits of its own long array RDID of the network. So when device is moving in the system, the good part here is that it can always obtain it and have it valid address. So if the device moves inside the single sync, changes the routes, the IP address doesn't change. But then when it moves under the different sync or under different gateways, potentially the sync address changes. So then the IPv6 address changes, which enables also the data coming correct gateway and correct sync when the downlink data is coming from the IPv6 network. So of course that requires also that the application is application servers are obtaining the new IPv6 address, but that's a normal IPv6 address change in what is happening in current IPv6 address quite regularly. So that's basically normal functionality of what the IPv6 protocol stack implementations are handling. So basically in the configuration data distribution, but then there is a header, there is a definition how the prefix information is provided. So there's basically the network prefix QA EULA 8 octets data provided to the device. So, and then this also enables nice header removal functionalities. So because this network, both device and the sync know what is the network prefix part, it's easy to introduce header compression or header removal functionality when sending IPv6 data. That data object can be easily removed. Then finally going to this little bit on this. So as mentioned, we have now this application profiles. We expect to see new application profiles, for example, this over the software update application profile, but also new ones. Conformance testing is under testing specification is under development. Good progress seen in previous meetings. Publication coming in spring next year. And then finally, let's spend some time for the spectrum regulation. So basically, European regulation activities are done in the CEPT, which is then followed by different regulations in other countries. Well, India, South Africa, some others in Middle East countries are good examples. But the CEPT contains all the EU countries and quite many other European and Middle East countries. You can Google the CEPT memberships, but it's more than the EU. So basically, there's a system reference document provided to CEPT. The recommendation for basically the new radio plus is the recommended technology for government drones. So UAS applications for 1880 to 1900 band and 1910 to 1920 megahertz band. So basically the core band of the Europe for DECT is this 1880 to 1900, but now this new band, new 10 megahertz 1910 to 1920 is now for governmental drones based on the DECT-2020 new radio. Currently, the CEPT is doing the preliminary assessment for this same band for general use cases, so extending it from the US to other parts. So we are expecting that will come available for DECT in Europe, which would be a nice extension, an easy one for implementation to support that one. And then FM60 is currently working on this new significant amount of spectrum on 3.8 to 4.2 megahertz, which is for the shared systems and the local licensing. And there, basically, the DECT-2020 new radio is part of the regulation. So there we expect also that future this technology can be used in that spectrum area. Then in North America, the FCC petition proposal is under work in a DECT forum. So basically the petition is for improving the system operation on US PCS band, which is this 1920 to 1930 megahertz, so 10 megahertz area very close to the European band. There is some improvements proposed for the DECT forum to modify the regulation slightly so that all the beneficial and potential of the technology can be used there. And then operation in the US 1950 megahertz band is supported already, so the unlicensed spectrum there. And then in Australia, for example, updated the regulation for DECT-2020 new radio by referring to this ETSI harmonized standard. So basically in Australia, exactly the same operation as in Europe is already now possible. Okay, so that was my presentation on this one.
Thank you very much, Juho. So next presentation will be given by Mirza.
So I give a short intro from the Mirza's and Jorge's work. So there's a setup simulation results then and the functionalities coming. So basically the content of the presentation is to study the selective flooding and downlink routing, how the basic functionality works, and then how we mitigate the flooding with the cast and selective routing and show some first results on there. So basically if we think about the selective flooding, so basically in the whole DECT-2020 mesh network relies on this cluster 3 as shown in the figure right, and where the nodes associate with their next hop to the parent node based on the cost value, and this is very heavily optimized for uplink data, so from node to the sink and to the backend. So basically when we have a sensor networks or devices in the mesh network where the majority of the data is going from device towards the backend, and the downlink flooding is then supporting the downlink direction, selective flooding where every routing node forwards the downlink packet to the every routing member unless the member is already in the final destination of the packet. So if we look the examples in below on the right side, so basically the good part here is that we don't need any flooding doesn't need any routing knowledge. It's immune to the mobility of the nodes basically because you just push the data downlink. The final data goes to the final destination to the same optimized rules as the uplink. So the likelihood that the data is received correctly and the links where the device is very good, same as in uplink, but there is additional transmissions, and if we look the example in the right in the top, we can see that in the selective flooding introduce one additional transmission in this example, simple example, 4 transmissions which are needed to reach the destination node and one additional transmission. So actually very small penalty of selective flooding. On the other hand, when the same setup of the network, very small one, just for example, but you have the destination node is the different one, you have 3 in unnecessary transmissions and 2 needed transmissions. So so the research question when doing the release 2 was how to reduce the flooding without expanding the network and node complexity unnecessarily, and how we can improve the system. And then in the next slides we saw that few performance examples what we have been obtained for the downlink routing. So Mirza, should you start now?
So here is a simulation scenario. So it is an indoor scenario, and we increased the area of this scenario to cases we analyzed. So first we can have a look of the parameters here, and I will not go through every parameters, but very important one we would like to address. So you can see the scenario, and the sink is in the corner, and nodes are deployed randomly over this area. So packet is 3 slots long, that is 6 sub slots, and transmission power is 19 dBm and 1.9 gigahertz channel frequency, carrier frequency, and we are using the whole RAS period, the beacon period, to transmit the downlink packet. And the sink is generating, here you can see my pointer here. Sink is generating packet to all nodes. It is transmitting to the router, and router, that is member router, and member router is flooding it until packet is received by the destined node. HARK is enabled. So almost every elements are there that is necessary for a good transmission mechanism. And here you can also see, have a look, I think, is it possible to increase the size of this figure? Or
No.
Just
No,
you can see this. Here are some stars. They are a router, and these circles are the nodes. We have 500 nodes, and the area is very big here for this case, around 100,000 meter square indoor scenario. So there are some dark green circle you will find. They are getting power above 50 dBm, and so on. Light green is getting this in this range, and orange is getting in this minus 72 to 87. But we didn't find any nodes that is getting power less than minus 87 dBm. So we can move to the next slide. Yeah. So it is the typical tree structure. I think it is for this 20 into 50 meter, 1000 meter square area for 500 nodes. Actually, all nodes that is are not plotted here because the figure will be messy, but it is represented in a different way. Only the routers are presented. The middle one is the sink, and all green nodes you can see are the routers. And inside the router, you will see a number, L something N. So from this figure, you can check that it means that if some inside the center, that is in the center of the router, you see that 5, 6, 7, 8, or 14, that means this router has 14 members or 10 members or 5 members. So this is the skeleton of the tree. And sink is generating packet and trying to reach every nodes. Yeah, please. Next slide. So what did we do in this performance analysis? Basically, we have taken two scenarios, 1000 meter square and 16,000 meter square area, 20 meter, 50 meter, 80 meter, 20 meter. And 500 devices are deployed randomly. And this network was formed autonomously. That is based on the smallest hop number. The node will be associated to the router. And transmission power is 19 dBm, as we mentioned before. So, and two scenarios, actually we mentioned 20 meter, 50 and 80 to 200. That is when we are expanding the area, this node, that is area is partially populated by the devices. And what is the effect? The effect is the hop number is increasing naturally because we need to provide the full connectivity of these 500 devices. So increasing the area basically increases the depth of the tree as well as may increase the number of hop. And this increase of the depth of the tree as well as the number of hops may change the downlink throughput or may change the amount of flooding, that is redundant flooding or unnecessary flooding, and it will affect the throughput. And the traffic arrival at the sink is Poisson's random process. The sink generates equal number of packets for each node in the network. Basically, what does it mean here? That is, the sink is not generating packet for any particular node. Basically, it is generating packet for all nodes equally. So if we have 10 nodes, total 10 nodes, for example, total 10 nodes in our scenario, and sink generates 100 packets in some time span between. So basically, it is generating on average 10 packets for each node. So it is generating packet for each node. Please go to the. So some comprehensive simulation study was done. It's a kind of average result, and average means for multiple run we average these things. So you can see that for 1000 meter square area, first row, 3 hops, 58%. 3 hops, 58% means 58% of node is connected with the sink by 3 hop. 40% of the node is connected to the sink by 2 hop, and so on. And we can see that downlink packet rate at very stability region, that is the amount of input and the service rate are same. So at stability region, it is 5 packet per second. And if we increase the area 16 times, 16,000 meters square, keeping the same amount of node, same transmission power, beacon transmission power, we see to contain or to have the full connectivity, the amount of 3 hop has increased. That is, we can see that 72% of the nodes are connected with 3 hops, 72%, 27% 2 hop, 1%. So that means that in order to reach 72% of node, the packet needs to travel a lot of hop. And when it is traveling so deep, that is, depth of the tree has increased, it also creates a lot of flooding. And when a packet will travel from sink to this node by traveling 3 hop, actually it will take time, the delay. So it is increasing the amount of extra flooding packet as well as increasing the delay for 72% of the node. That didn't happen for this first scenario. 58% nodes are 3 hop apart and 40% are 2 hop apart, means packet are getting 40% of packet and need to travel 2 hop. So anyway, so we can see that downlink packet rate decreased to 2 packet per second when the number of large hop is increasing and the amount of nodes connected with large hop is increasing, and it is increasing because of the increase of the area. And it could happen for a lot of reasons, but here increase of the area and to provide the full connectivity. Anyway, so it gives kind of indication that for the selective flooding, what could be the typical throughput for this 500 nodes, or this kind of, so of course it's a difficult scenario. But anyway, apart from this, we are studying further a more difficult scenario, suppose 100,000 square meter and or greater area, or for 1,000, 2,000 nodes, more hope, then what will be the performance of our selective flooding, and what could be the challenge, what is the bottleneck, provide bottlenecks, or how we could get rid of it. This will be studied, and I think some methodology is proposed already in the release 2 to address these things. And if Juho, please address that what is the standard proposal or methodology.
Okay.
Address these
So,
challenges.
yes. So just to highlight two things on the results also, that if you wonder why there is only 2% or 1% connected to the directly the sync, the number of devices connected to single other router, including the sync, was limited to the maximum 14. So basically, basically, even if there would be devices directly able to connect from the radio link point of view to the sync, they would not be allowed. It was only that every router has only 14 members. So of course, if you would allow more members to join, the depth of the network would go smaller. So you would have more devices with the lower number of hops. But it was just design choice here to go. And then, of course, also that this 5 PPS to make it some reflection. So we have 500 nodes. So 5 PPS means that you can transmit any node 1 packet in every 100 seconds. So a bit less than, let's say, less than 2 minutes. You can address the downlink for any of the device. But it's a completely different value that we were seeing in the previous case when we were looking the uplink data rates. So in the uplink we have been seeing much higher uplink data throughput values, and that's why we are addressing now the release to the basically the downlink routing. So how we mitigate the unnecessary transmissions of the flooding. So the cached routing is the first feature. So basically any routing node can record which of the routing members to forwarded certain destination uplink packet. And then the downlink packet can be the same destination node is sent, only that there are routing members. So in here in the example, for example, the sync has the cached routing functionality running. It's recording that node 3 uplink packet is coming via node 1, and the sync then sends the downlink packet to only to when the downlink packet node 3 is to be sent, it sends only to packet 1. And as you remember in the previous, we saw that okay, there would be this additional transmissions going to the other direction. In the same example, simple example, now we don't have any additional transmissions. And of course, this is very nicely working. And what is foreseen to be how this works is, for example, when we have an end-to-end ARQ functionality running, and the sync and the gateway basically are sending the acknowledgement that this data and certain amount of data has been received correctly to the certain node. So basically the response comes immediately. So then of course the possibility that the node has moved to somewhere else is diminished, and also that there is the amount of information needs to be stored in different devices is also lowest possible level. Also in other applications where we have an application sending first some uplink data, and then the application server immediately is responding to that data, basically allows the same functionality. Basically the memory size of the cached routing table is fully router implementation dependent. And also the router has to consider how long it should keep this records valid, needs to be considered based on the use cases and implement all deployments. And also the implementations may consider different strategies about which routing entries are maintained. and as the functionality is not visible for the other nodes. So it's fully backward compatible, works even if fractional set of nodes is supporting this feature. And as said, expected when there's rapid response from the application or end-to-end ARQ. Which, for example, the end-to-end ARQ would make the system work so that there would not be any uplink data losses at all possible, even though we have a possibilities that you are like we have in the release one ARQ between each link. You might have, of course, the situation that some node is having buffer overflows, some other problems in the and the retransmissions are not anymore working. But when we have end-to-end ARQ running, then there's not that kind of things can be also recovered. Then the second feature is the selective flooding, as mentioned. Basically, the node registers to associated sink, so that with the sink, so when they have associated, so the sink knows the topology. So the node indicates that which is a parent node to the sink, and the sink can create the full tree downwards. The basic this has been used also by other standards, but the basic problem there is that you don't have mechanisms to limit how deep you want to have that routing happening, and that introduces the problems of how many hops the system can have, and also introduces the packet overhead, because in the packet you are telling that what are the next hops where the data is transmitted. So the nodes doesn't have to have that in the memory. But in DECT-2020, the system was improved by so that there is a possibility to limit the number of hops and branches where this functionality is used. And if the device changed outside of this defined hop count inside the same branch, there's no need for registration, so there's less registration messages. Shorter routing path is included in the downlink packet, and if the destination is not yet reached, the remaining branch is then flooded based on the selective flooding or based on the cast routing. So, but basically, you can think about in the previous examples that the selective routing is used from the sink, or from the sink to the second level. So the first big portion of the flooding is already avoided. Then the second hop can be also used, or the third hop. But you can think about how many hops you want to have it, and then you can also optimize the number of registration messages. So this is now showing the examples. So in the example A, the branch is applied source routing, other branches are applied or based on the selective. So only in this part of the network the selective routing is used, or in the B where the selective route is only with this first hop level. So if the node, for example, in the from here to moves to here, it will register because it moves to the different branch. But inside here, any movement or mobility doesn't make any difference, because data going to this node will always come to this branch. And then in the second example, the same branch is extended to 2 hops. So basically, if this node is moving under this node or from here to here, it doesn't make any registration. But when it moves to here, it makes the registration, because the data, instead of data going to this part, it needs to go to this part, so that this also gets the correct information. So it enables us to, in the systems, to keep it sensible level. It doesn't make all the next hop changes to make the registration needs, and the amount of information also stored in the sink can be managed so that it's not too extensive. Then we have some case of the simulation of the first hop related cases. So basically, here the cluster tree with node count is randomized between 500 to 1000. So depending different runs has slightly different random number of nodes between 5,000. Simulations with the 3, 4, and 5 hops. So the first is the 3 hops, then middle is the 4 hops, and maximum depth is 5 hops. And the percentage of avoided transmit is compared to the selective flooding. So basically, you can see that if we have a depth of 3 hops, avoided transmissions is 80% in 40% of the cases, and then it starts to increase. So we have like very rapid increase of the avoided transmissions, and very minimal amount of the transmissions where we don't avoid any transmissions by having the first hop. And when the depth is of the network is increasing, the avoided transmissions is not exactly same. So we have larger portions where we don't avoid any transmissions, but it's reducing the amount of transmissions very heavily. Even if we use this for we do the selective flooding in the other hops, but in the first hop we just do the selection either based on the cached routing or based on the source routing that we avoid the transmission. We just provide the data to the correct next hop from the SIG. So there's a huge potential to improve the downlink capacity and the system performance by these features. And gradually, the implementation can start from doing it first in the SIG and gateway level, but then going further and improving the implementations further by doing cached or selective routing in the more depth in the systems when the need of the downlink data is growing. So in summary, we have currently the selective flooding, which is appropriate for delay-tolerant low-throughput networks when the downlink traffic is low, and it's practically agnostic for mobility effects. It introduced high number of redundant packets in the network, reducing the spectrum efficiency and energy efficiency. So that's the downside. It's very simple, of course. And then now we have released to the cached and selective routing for the mitigate the selective flooding effects. And even with the first hop routing, either cached or source routing, we can obtain significant improvement to the system. And of course, presenting more details and studying more details is our targets, and also looking from the product side. I think this summarizes our presentations, and then we have a Q&A secondly. So I think we can move to the next one.
Yes, okay. Thank you very much, Mirza and Juho. Next presentation will be given by Yasintha Rumesh from VTT. The title of the presentation is System-Level Modeling of Energy-Constrained Devices. Please go ahead, Yasintha.
My name is Yasintha Rumesh, and I'm from VTT Technical Research Center. And here we are presenting the results for DECT 2020 system, the system level modeling of these energy constrained devices. So for the introduction, the DECT 2020, it's wireless mesh network topology designed to support various machine type communication use cases. The network consists of fixed termination points, FTs we identify, and multiple clusters of radio devices connected to this FT, fixed termination point, via the cluster coordination devices, that is RT-FT. DECT 2020 relies on some of the radio devices acting as these cluster coordinators, RDFTs, to relay this data through the network, while others act as cluster members. So here we analyze the energy consumption of DECT 2020 networks deployed for different traffic models using system level simulations for the energy constrained devices, and what are the impacts of these traffic models on these devices. So first I will go through the abstract of the DECT frame structure and the interconnectivity between different node types. So DECT frame consists of these slots and sub slots. So these FTs and RDFTs sends beacon messages in their own beacon period and listen to cluster members during the remaining period, which is called the random access channel period, or the RACH period. The FT and RDFT sends out beacons at certain intervals to inform their cluster members of their presence and transfer the system informations. And we call them the cluster beacon messages, and radio devices. The DECT 2020 that promotes they can the radio devices, they can change their channel based on their role. So either in FT mode or the PT mode. When they are cluster members. So when they're cluster members, the radio devices listen to their cluster coordinator messages and transfer the packets in its buffer. What the RDFT does is it's relay these message packets to FT once they receive it from the cluster members. The mesh network topology allows different connection between RDPTs and FTs, and as well as between RDFTs as well, with possible multi-hop connections. So the figure shows only an abstract of those connections and how the communication happens through that one particular connectivity. So for the simulation, so for our analysis, we have considered the following deployment scenario for the simulations, and we have considered deployment scenarios with 7 sinks. It's FTs and 25,000 radio devices, and only 1% of these radio devices will be acting as RDFTs. So it's around 250 devices, and 80% of the devices were indoor devices, and 20% were from outdoor devices. And we use the frequency of 1900 megahertz and 5 frequency channels in the network. And also we assume the mean inter-arrival time of packets to be Poisson distributed, and here the selection of RDFTs, we selected them. We selected the radio devices which act as RDFTs randomly. So there's no specific criterion during the selection of FT mode of radio devices. So that's that was random. And the figure shows the devices node distribution. So the blue indicates the FT fixed termination points, and the red cross markers are the RDFTs in the network that was selected randomly during the simulations. And the remaining devices are the cluster members, RDPTs. For the simulation parameters, we considered different packet arrival rates as well as different packet sizes, because they could affect resource consumption in the network differently. And so these 25,000 devices, they were randomly distributed over a radius 690 meters radius circle, so which is an approximately around 1.5 square kilometers. And we considered the beacon period to be 4 seconds, and different stretch durations were considered for this beacon period. And during the stretch period, FTs and RDFTs listen to their cluster member and receive packets. So we varied them between different number of slots from 96 to 480, 4,800 slots. So it's almost half of the beacon period. And packet arrival rates and the transport block sizes varied to simulate different traffic intensities. So these transport block size represent the maximum number of bits that can be carried out from their respective slot counts. And for the energy modeling, so we integrated energy model to our simulator based on the flow of the current and time during different states. So these energy parameters, they were taken based on the previous study, and we the table summarized those values. And so the battery capacity was very small, around 5 watt hours, and voltage at 3.7 volt. And so this battery capacity that ranged between small battery, AA or AAA battery, which is lower than most of the smartphone batteries capacities. And we considered different current states, including sleep and receiving and transmitting states. And the transmit state current model was derived using a linear transmitter current model, and which is based on the transmit power. So in the simulation, we did not consider any power control method. We used fixed transmit power for the devices, that is the max transmit power 23 dBm. So after the simulation, to determine each device's battery life, we extrapolated the energy consumption during this simulation time until the battery is fully drained. And the results. So the this figure here, that shows the expected battery life of RDFTs with stretch durations. So different curves correspond to different packet arrival rates and packet sizes. And the RDFT battery life is distributed in a number of days with higher traffic intensities, reducing the battery life. So the traffic intensity is less than 1 packet per hour device. Shows similar battery life variations regardless of these packet size. The RDFT battery life is mainly the curve shows this RDFT battery life is mainly affected by the rest duration in the network, and the interesting thing to note is this behavior is only observed only in RDFTs, and which is they are around 1% of the device in the network. So that's a considerably low number of devices in a network of this number. And for the RDFTs, RDPTs actually, so the figure next shows the RDPT expected battery life of RDPTs with rest durations. The curves correspond to different packet sizes and packet arrival rates, and compared to RDPFTs, RDPT shows higher battery life that is distributed in number of years. And RDPT battery life is over 10 years for most of the traffic configurations, except for this high traffic intensity with large packet sizes. And for lower traffic intensities, battery life for RDPTs were quite similar and over 18 years for all the rest durations and the packet sizes, and the RDPTs they are 99% of the devices in the network, which means most of the devices in the network consumes very little energy and have a larger battery life expectancy as well. And so we observed a significant behaviors for this high traffic intensity scenario, that is 10 packets per hour per device. Therefore, we further analyzed the energy consumption of this scenario, since the other seems to have a much smaller and much similar behaviors, and this figure shows this battery life expectancy in high traffic intensity environment with rest duration and different packet sizes. The rest duration in here is depicted as a percentage of the beacon period, and the battery life is spanning over several days as per the figures, and when the rest period is around 50% of the beacon period, the battery life actually reduces down to battery life to 2 days, and also this result shows that the increased packet size also affecting the RDFT's battery life, and this suggests that the RDFT mode selection should consider available battery capacity when it is selecting the FT mode, or it should have a larger capacity, since during the simulation we only considered battery with much lower capacity, that is around AA batteries, or RDFTs can have a longer battery life if it is have this energy harvesting capability, so it can regenerate some of the lost energy. Also, if the RDFT is connected to a power source, this constraint is eliminated as well. So the energy consumption for the RD PTs. So similarly, this figure shows the battery life expectancy for the RDPTs for different rest durations and packet sizes. The RDPTs have a lifespan around 5 to 70 years, depending on the use case. increased rest durations have helped to increase the RDPT's battery life, and larger packet sizes lead to a higher energy consumption for RDPTs due to this increased transmission time in the network, and they cause reduction in the battery life. And but comparatively the RDFTs, the RDPTs have higher life expectancy, and this is the behavior for most of the devices in the network. And now, if we consider the network performance, so with the rest duration variation and the packet sizes, we observed the changes in the collision probability in the network performance. There is the increased rest durations. We have seen that with the increment of the rest duration, the collision probability reduces, and also the large packet sizes, they tend to increase the collision probability due to longer transmit time. Yes, these are the network performance. We observed significant variance in the network simulation. So as a summary of the simulation results, most of the RDPTs had a battery life over 10 or 18 years, except for large packet sizes in the high intensity traffic conditions. RDFTs have battery span of several months in low intensity traffic conditions. In high traffic environments, increasing rest duration reduces the RDFT battery life, even though we reduce the collision probability. Due to the nature of this medium access protocol and the routing responsibility, adds an additional energy consumption to the RDFTs. This suggested that the RDFT should have higher battery capacity or energy harvesting capability, or it should be connected to a power source. The thing is to note here that we assume the RDFTs are having a similar battery capacity as RDPTs, which is much smaller than the average smartphone battery. So that is why we see this kind of results for the RDFTs actually. Yeah, and that is all the results I have, and thank you for your attention. So
okay, thank you very much, Yasintha. And we go to next presentation that will be given by Robert Walstab. And Robert's presentation is Channel Aware Multi-User Resource Allocation to URLLC. Please go ahead.
So yeah, thank you for your introduction. I'm Robert from the University of Technology in Dresden, Germany. And as Mika already introduced, I will talk about the channel aware multi-user resource allocation for the URLLC use case. So, as in the last presentations, we already talked about industrial applications, and these industrial applications demand ultra reliable low latency communications. They are the URLLC use case, and there are different state-of-the-art methods to achieve this URLLC. For example, multi-connectivity or other FDMA technologies to benefit from frequency diversities. But if we have limited available bandwidth, this scales badly for large user groups, because every user then needs additional bandwidth, and this goes on and on and on. So in this use case, especially if we have large user groups, it is really important to use the available bandwidth as efficiently as possible. So, and there we have a proposition. So we know that the channel conditions vary by precision. And that means that a resource block in frequency or in time does not perform well at one time slot. It may perform well at a different time slot. And in addition to that, this is also different for different users. That means one resource for user A may be not suited for the communication, but the same resource is really ideal for user B. So what is our proposition? We now want to allocate our resource blocks for each time slot and each user individually, and do that to achieve our goal of having our ultra-reliable communications. So our goal is now to minimize the outage rate, because we are in this environment, and we do this instead of maximizing our throughput, which is often the optimization goal in standard mobile communication schemes, for example, 5G, etc. So in order to achieve our goal, we want to maximize the channel gain of our weakest user, because if we maximize our weakest, so if we get our weakest user above the threshold, then that the user receives the data, that means every user will receive the data, because otherwise the weakest user wouldn't be the weakest user. So to achieve this goal, we have different radio resource allocators. On the one hand side, we have the channel unaware resource allocators, and on the other hand side, we have the channel aware ones. So channel aware in this context means that the scheduler or the allocator has channel knowledge. That means we have to measure the channel beforehand and then use this data to allocate our available resources. And in the channel aware allocators, I want to introduce to you an optimal allocator and multiple different so-called preference-based allocators who do the channel aware allocation too, but in a more more practical way, because the optimal allocator is quite resource intensive, and yeah. So, but first I want to introduce you to our system model. So in our system model, our users are represented by AGVs, so automatic guided vehicles that are driving over an identical course. So we have a kind of procession of different AGVs driving behind each other with an identical distance. So we achieve our spatial diversity by shifting our users in time. That means we have one data set of data that can be measured or simulated. I will go into that later. And we know that the channel is correlated for these users. That means the channel for user B at the same position that as for user A is identical. That means if the user B reaches the same position as user A 5 seconds later, the channel roughly looks similar. So that means we achieve our spatial diversity by shifting the channel data in time. So then we allocate the same number of subchannels, that means the same bandwidth, to each user, and now we model our user outage. So we do this in a really simple way, just to compare our allocators quite easily, just by comparing the allocated power with a so-called power threshold. And if the allocated power is larger than this threshold, we assume that the communication is successful, and if not, we have a user outage. And as we have equally important users, a user outage, the outage of one single user already means a system outage. Now we come to our allocators. So I will want to introduce now the baseline allocators, where we compare our allocators against. So we have the best possible algorithm. Here, every user gets allocated their best performing subchannels. However, of course, the one resource can also be the best resource for multiple users. So we have collisions, hence the name possible, but we wanted to have an upper bound to compare our allocators against. And then we have the optimal allocator called Trussell in this case that I introduced before, or I told you before. And this allocator utilizes graph theory, more specifically the Dumas-Mendelssohn decomposition, and it finds the optimal allocation by that meets the min-max criterion. However, this is computationally really expensive, so it might not be usable for a low latency application. And other than that, we have the conventional methods, or then these are the channel unaware methods that don't need any channel information. We call them static consecutive because we just allocate the resources once, and we are done. And in the static consecutive, we just bin adjacent subchannels and then allocate a large subchannel to each user. On the other hand, we have the static interleaved. It's also static. That means we only do the allocation once. And here we spread the subchannels that we allocate evenly across the available spectrum, hence interleaved. And we do this to benefit from the frequency diversity of our channel. Now I want to introduce the most interesting allocators, and this are the preference-based allocators. So when we allocate these subchannels, we know that the performance of the user, that means the power that the user, so the power of the channel that the user will, or the quality of the channel that the user will see, depends heavily on the resources that the user gets allocated. And so to identify the weakest user, which also depends then on the resources that the user gets allocated, we do an iterative approach. That means we measure the channel for every user, and then for each user we sort the subchannels by the SNR or the channel power to obtain our preference list. And now from this preference list of each user, we calculate a quality metric Q for each user. How we are calculating the quality metric, I will show you in the next slide. So, but for now, for the user for the minimum or the least quality metric, we allocate now the preferred subchannel for this user. That means we look again in our preference list where we have our sorted SNRs, and that user gets allocated the best channel from this list. So because now this channel is allocated and therefore blocked, we have to remove this channel from the preference list of all users. Then we look if you have users with an incomplete allocation left. If we do so, we repeat this process. Now we have to calculate the quality metric again because now the preference list of each channel has changed, and we repeat this until every user has got allocated the channel that they need. Yeah. So let's look into how we calculate our quality metric. We have different methods to calculate our quality metric. For example, the pref single or the preference single. Here we only look at our best channel, and the quality metric is just the power of the best channel. However, this only captures, of course, the best channel of this user and not the whole picture. That means it is really possible that a channel might have one really strong subchannel and therefore always gets a really good quality metric. And a good quality metric means that this user does not get the chance to choose this channel, because remember, we always allocate the subchannel to the worst user. But as soon as this channel gets allocated to another user, this user is really screwed, so to say. That means we need a metric that better captures the whole channel for every user, and therefore we look at the preference window. Here we sum the best L channels to have an idea about the L best channels. And in addition to that, we introduce the pref gradient. Here we multiply the best channel with the Lth channel, which roughly represents the gradient of this preference list. So how fast the channel deteriorates for each user in this preference list. And the last allocator I want to show you is the pref weighted, which is really similar to the pref window. However, we weigh the different powers of the channel before we add them, and our weights are represented by the channel. So we obtain our rates by looking at the correlation of our subchannels. So at the beginning, where I introduced you the channel aware allocators, I told you that we do we only allocate a single resource each iteration. But now we want a different way to look into this is just to allocate every all resources that we need to each user at once to save on iterations in our iterative approach. So, but what data do we use? So, for example, we did use channel measurements. There we used different measurement campaigns. The first one was a measurement campaign in an industrial setting at the company Bosch in Hildesheim, Germany. This was a small factory hall where we drove our AGV, which you can see in the middle picture, across a predefined track. This data set is published and can be used for your simulations as well. And in the USWA project, we extended this measurement with one of the USWA partners, SEW, in a bigger hall with more scenarios, with more data, on different tracks, longer tracks, and we're currently working on publishing that too. But in addition to the channel, in addition to the measure channel, we also wanted to look into synthetic fading or analytical fading to better picture different channel characteristics, mostly different coherence bandwidths, because we found that the coherence bandwidth might be the most important parameter of all this allocation stuff. So for our synthetic fading, we looked into our measured channel data, and we found that the measured fading can be modeled by a Rayleigh fading channel, because we mostly have non-line of sight conditions. So for generating a single fading channel, there are multiple methods. For example, the sum of sinusoids method and the filtered Gaussian noise. So therefore, it is really easy to generate multiple Rayleigh fading channels which are not correlated. To now get them correlated, we used a method proposed by Tran and different authors, where we have a desired covariance matrix that we obtain from our measured channel data to just remodel this channel. And then we calculate a coloring matrix to color, so to say, our uncorrelated single Rayleigh fading our uncorrelated Rayleigh fading channels to obtain multiple correlated Rayleigh fading channels. So on the upper right hand side on the slide you see our covariance of the subchannels that we obtained from our measurement data, and with that we colored our Rayleigh fading channels to get our data for our simulation. So of course we had to verify the synthetic data by comparing our allocator performance in the measured data with our synthetic data, and we see that the performance of each allocator is the same compared to the synthetic fading. And here you see the first glimpse into the results of our allocators. You see that the static allocators perform the worst in our simulations. That means for an identical outage power threshold, we only achieve a really subpar outage rate in our system. However, the preference-based allocators really offer a benefit in this kind of environment. For example, pref single outperforms the static consecutive allocator at every outage power threshold and outperforms the static interleaved one for the hour outage power thresholds. And our preference gradient allocator almost reaches our upper bound of the best possible allocator. That means it really almost gets the best performance out of our channel. We can look at different coherence bandwidths too, which we can because we used our synthetic channel data, and we see, of course, the higher the coherence bandwidth, the lower the outage power threshold is for the desired outage rate, and that is represented in this graph. Here we plot the outage power threshold needed to achieve an outage rate of 10 to the power of -3, and that means a lower outage power threshold is worse than a higher power outage threshold, because that means we already experience an outage for a low power outage threshold, and yeah. So that means for every allocator, the performance deteriorates with more coherence bandwidth, but we see that for all coherence bandwidths, the allocators that have the channel state information, that means which are channel aware, outperform our channel allocators without the channel knowledge. Yeah, but of course, employing a channel aware allocator and doing this allocation means that we have an additional step in our computation to allocate, and these steps of how many steps we have to do is really dependent on how many users we have and how many resources we have to allocate. So how do we improve the speed of our allocation? By decreasing one of these numbers. So if we merge adjacent subchannels, so we bin subchannels that are adjacent to just a single subchannel, we reduce the number of available resources. So and we see that for all allocators, of course, reducing the number of available subchannels by binning deteriorates the performance as well. However, this performance penalty really just starts to show if the subchannel bandwidth reaches the coherence bandwidth of the system. That means we can merge our adjacent subchannels without having a large performance penalty when we are still below our subchannel bandwidth. And A different allocator that I introduced was the bulk allocation, where we don't only allocate a single resource for each iteration, but rather allocate all resources at once. And here we compare this bulk allocation for our different preference space allocators, and we see again that the performance only suffers by a fraction of a dB for every allocator. And that means again we can reduce the number of iterations in our preference-based iteration loop by quite a factor, and don't suffer much performance loss. And now I talked a lot about the performance in regards to the outage rate, but let's look at the performance in regards to the computational effort, because we are again in an ultra-reliable low latency context. I talked about the ultra-reliable part. Now let's talk about the low latency part. And we see that our optimal allocator, the trestle allocator, really is not that good in this regard. While it achieves low outage rates, it also takes a really long time to do this. Please be aware that the y-axis here is logarithmic. That means our optimal allocator is 1,000 times slower than our preference-based allocators, which are of course much slower than our static allocators, because there we only do this allocation once and don't need to measure the channel and then calculate a quality metric and so on and so on. However, the bulk allocation also reduces this computational effort again by, as I said, reducing the number of iterations. So let's summarize this presentation. Considering CSI and measuring the channel and keeping this the channel state for every user in mind significantly improves the outage rates in comparison to static allocators that are channel unaware. And our preference-based allocators do this in a much faster way than our optimal allocation. And the bulk method additionally improves the compute time while only punishing the performance by a small degree. And the allocator that we identified at the best allocator was the pref gradient allocator. That was the allocator that multiplied the first and the 11th subchannel of our preference list, and therefore looked at the gradient of our preference list. And we want to recommend the preference gradient bulk allocator, which has similar performance to the pref gradient allocator, but does this in a much faster way. So, one outlook for you. In this presentation, I showed you our performance only for users getting allocated an equal number of subchannels. However, if you look in a scenario where one user is located really near our base station, this user does not need that much bandwidth to meet its power criterion, while users at the edge of our coverage map really need more bandwidth to be able to communicate with the base station. So the next step would be to have another degree of freedom in our optimization problem, which is a variable number of subchannels per user. And with this, I'm at the end of my my presentation, and I see that I have still some time. So if you have any questions, please write them at the FAQ part, so that I'm able to answer them directly here. Yeah. Thank you.
Thank you very much, Robert. So Joonas will give a talk on DECT 2020 new radio link distance performance in varying environments, models and measurements. Please go ahead.
Thank you, Mika. Can you share see my screen?
Yes, we can.
Okay, good. So let's get started then. So hope you still have a bit energy for the last presentation. It's been some nice results so far. And in this presentation, I'm going to be presenting you the results that we have achieved and found out in some practical measurements that we've been doing during this year within this project. So let's get started. So this is the overview of my presentation. So giving you first a bit of a background on how we ended up doing these measurements. Then the actual measurement setup and procedures we had related to that one. Then we are going to look on the different scenarios that we were actually measuring, these different environments. We were performing these measurements and then checking what kind of results we then ended up getting from those and some conclusions. So yeah, that was the overview of this presentation, and as you know, within this USWA project, we are generally interested in seeing how we can utilize this DECT 2020 new radio technology. And as the project started already a couple of years ago, at that time we didn't yet have these devices in the markets. But as soon as those were available, then of course we wanted to test out and see how we can then utilize those and in the beginning see how long we can go, so to speak. So in mesh networks, you could then consider that as a one-hop distance that you could reach. And that's of course something that is interesting to see, that how large networks then you need to build to cover certain areas and distances. So now we are only focusing on point-to-point measurements with basically 2 devices. And for that, we were of course then considering different KPIs. So seeing that what we were able to actually measure and what we can then actually say based on those measurements. You have to take into account several things like what kind of transmission powers you can use or need to use, what kind of antenna heights you have to use, and so on. And of course, we were also considering that for this kind of a one link, the success rates are good when we have above 90% success rates available. And at the same time, we are of course checking how does these compare to some general propagation models. So how close they are to that and in general. And before I forgot, these measurements were performed by my thesis worker Mohaiminu Haig. So he was doing these measurements together with a couple of summer trainees. But yeah, let's see what we then actually have here. So the typical setup that you can see over here on the right side is this cheap development kit by Nordic Semiconductor, this NRF 9131. So we had 2 of those. We attached antennas into them and placed them to tripods. Okay, we had some 3D printed cases there as well, but that was the basic setup. So you attach it to tripod, and then you have a laptop that provides power through USB cable, and also you control the functionality that you do with the device. So you initiate the transmissions, receptions, and so on. So okay, you have 2 of these, one for the client or the transmitting side and one for the server or the receiving side, to really then test how does the connection work between these devices. Then of course some other devices that we were using to accurately find our distances, laser distance meters for indoor locations, mostly outdoors, then using satellite-based positioning to see where we are, and maps as well. Those laser distance meters don't work for so long distances, so that's the reason for that. And in the end, I will also say a few words about what was the state of the spectrum when we were measuring these. So we also check that situation as well. So some general parameters as well still to cover. So as you can see, we were naturally making these measurements at the DECT channels. So around 1900 megahertz with this 1.7 megahertz channel bandwidth. Then we were using transmitting powers that were available with these devices. So from minus 20 dBm up to plus 19 dBm. So slightly depending on the location, adjusting that one. And as a general node height that we were using this 1.5 meter height for the antenna. So that's quite typical, for example, for a UE height in mobile networks. But here we were using that as a kind of a reference value. So it is actually relatively low. So a few words about that later on, specifically for outdoor areas. But that's like the value we used quite often in these different areas that you can already see slightly on the right. Let me just take my pointer here as well. So in different areas, it was set up to this 1.5 meter. Then some general parameters, antenna case and so on. Perhaps the most interesting here that for each distance that we measured, we had 5 minutes measurements performed with 1 second successive packet transmission interval, meaning that in the end for each distance we had 300 samples to study. And we were checking both the PDC and PCC, so the physical data channel and physical control channels, as was available with this software we were utilizing. A few words about that in the upcoming slides. And of course, when you're making measurements in different areas, you are interested to see how do they compare to some models that we have for these signals. So if we first see here the table here, so this is by 3GPPs, this 38.901. So we have slightly different models for different use cases indoors. So as we were making a lot of indoor measurements, then we were comparing it to those. And then for outdoor, of course, you cannot use these models. Well, you can, but then we were using other models that are more suitable for outdoors. Always you have there in the base, free space path loss model, but that's like very basic stuff. But as a kind of a reference value there all the time, but then with some more sophisticated values, taking into account the limitations of those, but it provides a bit of a more insight into where we are when we start to see the results. The procedures were quite easy, straightforward in the sense that you go to, of course, your plan first where you will do the measurements, then you go there, set up everything, adjust these parameters that you want. So we were using the Nordic's own software there that was available for us. So you define the transmission powers, all of these different options you have available for the transmissions. And then you do the measurements, store the values, and finish up. Okay, typically you then repeat that for several distances in a location, but that's the general idea. And then as for post-processing, we were using MATLAB a lot to just, analyze the results. You need to parse through the files and the usual. And that's a way to then start analyze what we were able to actually find out from these measurements. So here's a quick overview first about these different locations that we were having these measurements being performed. So we were around this Tampere region here in Finland. So a lot of measurements were focused into this Hervanta region. So we have our university here, but then we also went to some lakes, some observation towers, and some industrial areas to really make all kinds of measurements. So there were plenty of those within this campaign, and they were focusing on these different, I would say, environments. So strictly indoors, mostly corridors, office areas, then between floors, so interfloor connections, then from indoor to outdoor, so being close to the windows inside the building, and then going outdoors at that area and see how far you can go. then between buildings, so this indoor to outdoor to indoor use cases, and of course a lot of outdoor use cases. So those were pretty much the different categories that we were focusing on with these measurements. But yeah, let's take a closer look on these different areas and perhaps highlight a few things in these different cases. There's actually a lot of these performed. I'm here focusing on some of these. You can find a lot more information. I will show you later in the last slides links to the places where you can find all of the measurements, but let's focus first on these use cases here. So this is our university campus here in Hervanta, and we were in these different buildings doing measurements. So within one floor in a corridor doing measurements, then outside doing measurements between the buildings, then from one wing to another wing, so this kind of a interbuilding measurements, and then between floors also. So a lot of measurements were being performed here at the university campus, where we basically started the measurements before going to the other locations. And you can here see some examples. So it's quite typical to see these corridors here. Then you perform the measurements there. You get something like this. So what kind of distribution of single strength values you have around different distances that you were measuring, and what kind of average values you were able to get from those. Or the same story basically converted into a path loss here, taking everything into account and seeing how those will compare to these different models, then visualizing the success rates and so on. But it's here mostly for an example, and we can see that then a lot of these kind of tables were also being provided out of these measurements, where you can then see a bit more clearly about what is the standard deviation per location between the samples, or the minimum maximum values, and this kind of statistical values are being then shown if you're interested in checking the results in a more closer view. But besides the Hervanta region, the campus area, we went to several other locations. So we are close by to Wirepas offices. So of course we also went there to see. There we actually did this kind of an indoor to outdoor, or indoor to outdoor to indoor. So you can see here. So between two buildings, we did some measurements as well. Just quickly going through these so that we have enough time for the results part. Then, of course, we, besides office areas, went to some industrial use cases. So we were inside a factory area in Valmet's factory. So there we had several different use cases that we were considering, the line of sight and non-line of sight use cases for different areas that you have available within the factory. So some interesting results also made in this kind of a factory environment. Then we have the kind of a suburban area, so we are starting to be closer to these outdoor areas. So just sidewalks within the city to see again how does the connection work if you would place it along these, or then if you would go closer by to some power lines. So these are more usually quite open areas as you have these big power lines going on there. So how well the connection is then working alongside these areas was one of these use cases that we were going through here. Then some outdoor parks. So one football field from end to end, we were checking how it goes. Or then if you are, just some park and see how you would have a connection to non-line of sight that has a bit mixed forest and lake there. How is that working? So these kind of a different use cases were selected here. Then, of course, a bit more special use cases where you are starting to see that, okay, how would this work over a lake, for example. So you go to the beach, set up the device at one end, and then you go to the other side and see how well it goes through. So that was quite nice test that we did. And then one of the last cases that we also did was this kind of an observation tower. So you go high up there and see how long you can go in an area that is relatively open. So that's providing some of the longest distances naturally when you take the other node quite high to the tower. But those were the basically the different quickly going through these different use cases that we were focusing on. So we can now take a bit of a closer look on the results, what kind of values we were able to get from these. Again, a bit of a summary of these measurements. More details are available in the publications then, but here highlighting, showing you a part of these results that are perhaps interesting to see at this point. So first, if we start to go through what is mentioned here, so we have the maximum distance with minimum transmission power. Okay, let's think about that a little. So how long can you go, but with the smallest amount of power? We are typically indoors limited by the size of the corridor, so how long we can go. So if we would use full power here, then it would work still, of course, but we can do with a smaller amount of power naturally. So that's why this kind of presentation of values over here. So a lot of line of sight cases with straight corridors, so different distances. So we had that 1.5 meter antenna height and different powers required to have this success rate of over 90% for these indoor locations. So if we want to see here something, how it's ranging, so when the power is from -20 to 0 dBm in this line of sight corridors, you can get from 40 to 190 meters. So quite a varying distances with this. Of course, there's a bit of a difference in the power as well. And then for non-line of sight cases indoors, as an example here, we have you can get over 60 meters with 0 dBm power. So quite interesting to start to see what kind of values we are able to get in this kind of some of the indoor areas that you was able to see there. Then from indoor to outdoor use cases, you have, of course, a lot of things that depend on the used material. So what kind of building you have, what kind of wall materials, what kind of window materials you have. So there you are not anymore so much, of course, restricted by the distance. So you can go outdoors as far as you can typically go, and then you're not limited by the space. So you would of course use the full power available and see how long you can go. And here with this couple of examples that you can see, you can get close to 100 meters if you have your node indoors, and then you have the other node taken outdoors and you start to go away from the building. And then what we also know that when you started to do this inter-building measurements, there you have a lot more variation coming up from the building materials. So perhaps just highlighting here that more measurements would be required in a different kinds of buildings. Specifically here in Finland, we have this selective surfaces in the windows, so there's a huge attenuation coming from the walls and windows. So there is really a difference to what kind of building you have in use and how long you can go if you want to go from indoors to outdoors and have the connection there to work well. And then of course the outdoor use cases. So we have here some of those areas that I was mentioning and listing down. So mostly kind of a free space areas in this line of sight areas, and then some non-line of sight areas if we were talking about those parks with forest and such. So here again we can see quite different distances with different powers, but if we would now focus on the full power versions, because we're interested in the maximum distances, so we can see here again, noting the low device height of 1.5 meter, we can reach, you know, already above 600 meters between the nodes, and even more, of course, when you start to have special cases where you have lakes over with where the signal propagates very nicely, and then specifically if you take your other node to very high, then you start to suddenly see a lot of increase in the link distances. Of course, you would expect that then when you would deploy these nodes that you would go at least to several meters high, perhaps to these street lights. So then these distances would be, of course, be quite a bit more than what we see here. So do note that they are with this 1.5 meter height. So that is something to also take into account or note when you're going through the results. Then a couple of slides about some results where you see how these different few chosen indoor models compare with the results that we were able to get. So this is something that you then start to see that how would a specific environment work with a different model that you have available. So what we can see here, for example, that in this Konettalo second floor corridor, we have consistently the lowest path loss received. There we had actually quite thick walls around us, so it was acting a kind of a tunnel-like. So those are something to, of course, take note when you are starting to analyze these results. And then a similar example for outdoor use cases with those that had the full power. So there we, of course, well, we had those more of a mobile network models there as a background, which are a bit pessimistic, and okay, they have a bit more limitations to their use, but we can kind of see here that where our measured values will fit between these models. And that's then useful information in deciding when you are evaluating that what would be a suitable model when you would use this technology. So what to expect, what would fit the most well here, or what would result in the best fit, so to speak. Perhaps a bit more interesting values are shown here. So this is taken all of the indoor locations and put them in one graph where you see an average value of one distance basically. So each marker here is a result of 300 samples. So a lot of measurements. So 5 minutes per point. But here we start to see how the signal strength and SNR, for example, the blue ones behave in these indoor areas in general, or how does the success rate then behaves as a function of the signal strength. So you can clearly see that this more quite typical behavior of this kind of a gradual increase of the SNR as the signal strength increases before it starts to saturate here. Whereas, of course, with the success rates, you have a more of a bigger drop after a certain threshold. You start to then have more challenges with the connection with certain lower SNR values, which is quite typical in these cases. And the same graph for outdoor locations. So you can here see perhaps a bit less variation if we compare to the previous one. You have more distribution here around the trend that goes here. So indoors you have a lot more different materials and you have more non-line of sight areas. So that is of course behind there, but here in outdoors you're mostly free space environments. So you see a tighter fit, so to speak, for these values, and a similar behavior here. I mentioned to where we see those values, how they start to change. So if we take an example, so the success rates surpassed 90% values when we are outdoors above 12 dB, roughly speaking. So there we start to see quite nice success rate values, and then of course when you go then below here, then it starts to drop quite fast. In all of these locations, we are actually we also measured with spectrum analysis, seeing that how did it look like, was there any interfering signals. So this was on there all the time, and we were checking how it goes. And as a comparison, you can see that close to the DECT band we also have the EUTRA band 3 signals, so those were pretty much always available. Here we have mobile networks operating quite nicely everywhere, so they are quite close by, but of course not providing so much interference to our intended bands that we take. And as a summary, wanted to highlight so the results that were quickly went through here. We now sent for publication for this EUCAP. It's already available. The kind of a preprint out of that in Arxiv. So you can see that from here, and a lot more of these results are in my thesis workers already published thesis. So there you can have and see from all of the different locations, all tables and all graphs. So there's a lot of details to go through there, which we of course didn't have time to go through here. But as a quick summarization of those results, we already started to see some interesting results also already here, and those were pretty much something that we then ended up putting into the conference paper, and that is then now waiting for in the review process. But yeah, I suppose that was roughly speaking my half an hour that I had prepared for you. So thank you. And now we have, it seems, some time for questions as well.
Yes, thank you very much, Joonas. Interesting results. So thank you very much for your participation and attention. It is nice to have audience for our results. And there is possibility to provide this feedback so we can take learnings. And also we like to acknowledge funding obtained for this project by national funding organizations listed there. I will still check are there any questions? I think there are not. Okay, so we are closing, and thank you very much still, and have a great day and week. Bye-bye.